All right, hello everyone. So today we've got a discrete math problem. We're going to prove that 5 to the n minus 1 is divisible by 4 for n greater than or equal to 0, or all integers greater than or equal to 0, or in that alternative notation, 5n minus 1 slash 4, which is just shorthand for divisible by 4 for n greater than or equal to 0. All right, so we're going to be using just regular mathematical induction here. There's also strong induction, which we won't talk about today. And the first thing we usually start off when we're working with these induction problems, and we like to write out our statement with like a notation, just to kind of keep track of things a little easier. So I'm going to let the statement be P of k, be the statement 5 to the k minus 1 is divisible by 4, excuse me, for integer k greater than or equal to 0, okay? And the first thing you have to work with mathematical induction is the base case. We have two things you have to work with, the base case and the inductive step. The base case basically says that the first statement, has to be true for the starting value of your claim. So if I'm saying my statement 5 to the k minus 1 or 5 to the n minus 1 is divisible by 4 for n greater than or equal to 0, well, mathematical induction says, okay, you need to show me that it's true for just 0 itself, because that's where you're starting off with. So that's why I'm saying P of 0 is true. So what I'm going to do is I'm going to plug 0 into my statement. P of 0, 5 to the 0 minus 1 is divisible by 4. Well, 5 to the 0 is 1. 1 minus 1 is 0. So is 0 divisible by 4? Yes, it is. So check mark on that. Okay. And my inductive step is the next part. And the inductive step basically says that if your statement is true for some value k, so for some integer greater than or equal to 0, then it's going to be true for the next value, okay? Or if you prefer P of k with the little arrow, P of k plus 1, like an if-then statement with logic. So the way this works when you're working with the inductive step, you're going to assume that your statement holds for some integer, k greater than or equal to 0. So I'm assuming 5 to the k minus 1 is divisible by 4 for some integer greater than or equal to 0. What I need to show is that the statement 5 to the k plus 1 minus 1 is divisible by 4. So that's what we mean by that P of k plus 1. And not always, but a lot of the time it's just like replacing the k with the k plus 1 value in your statement. So that's how that would work here as well. Yeah, because if you're telling me that P of k means 5 to the k minus 1 is divisible by 4, then P of k plus 1 means 5 to the k plus 1 minus 1 is divisible by 4. All right. And this part sometimes requires some ingenuity on your part, and here's how that works here. I want to work with 5 to the k plus 1 minus 1, and I want to involve the statement 5 to the k minus 1 divides by 4. You always want to try to involve that hypothesis, okay? So how do I do that? Here's what I'm going to do. I'm going to go ahead and rewrite that minus 1 at minus 5 plus 4. Why, you say? Well, here's why. 5 to the k plus 1 minus 5, I can factor a 5 out, and I'd have a 5 to the k left, and a minus 1, and a plus 4. Well, 5 to the k minus 1 is divisible by 4 by the hypothesis, and therefore 5 times 5 to the k minus 1 is also divisible by 4. Right, if I told you something's divisible by a number, so for example 12 is divisible by 4, then 5 times 12, 60, that's also divisible by 4. That doesn't change the divisibility of it. So this statement is true. And therefore 5 times 5 to the k minus 1 plus 4 is also divisible by 4. And why is that? Because if you add two things that are divisible by 4, then that sum is divisible by 4. Yeah, 4 divides 4, it goes in once. And as we just talked about, 4 divides 5 times 5 to the k minus 1. Or if you prefer using the notation that I'm working with, it looks like this, okay? And therefore, we have shown that P of k implies P of k plus 1. My E there got a little wild there. P of k plus 1. And therefore, 5 to the n minus 1 is divisible by 4 for n greater than or equal to 0. So this last step, let me speak about what I just wrote. Now I'm saying that this statement holds for every number now that is greater than or equal to 0. And why am I able to say that? Because what I have shown is that because the first two things that I showed the base case is true, and I showed that the inductive step is true, which implies that if any one value is true, then every one after that value is true as well. So if P of 0 is true, that's what the base case said, the inductive case step will tell you, well, if P of 0 is true, then P of 1 is going to be true. And again, the inductive step would say if P of 1 is true, then P of 2 is true, and etc. P of 2 implies P of 3, and that goes on forever and ever. So that's why mathematical induction would work here. Okay, so I hope this helps, and I'll link another video that I made, several examples out there with mathematical induction. And one last thing, yeah, this move over here, the 5 to the k plus 1 minus 5 plus 4, let me circle that here. Yeah, that's not an easy move to get like the first time. It's just something you learn. So if you thought I just, pull that out of a hat, yeah, sort of, I did. If it's your first time seeing this, but you do this a lot with these types of problems and other problems where you rewrite a statement so that you can use some statement that is true. Like, so for example, I wanted to use that 5 to the k minus 1 was divisible by 4. I was not going to get that from here, so I needed to work with something, and that's how you use that. Okay. All right. Well, thanks for your time.